The tension must be mounting. I've been leaving our star poised with the core collapsing, and we haven't asked what happens then. And so core collapse is going to be the next topic, obviously. And so what happens when the center of a star collapses? We have this solar mass, few solar masses of solid iron-rich core collapsing, and it starts with a sort of typical stellar core size of the Earth, and it collapses down, it turns out, dramatically in about 1/10 of a second. It collapses to a size of a few kilometers, and we'll talk about the remnant in a later clip. But this gravitational collapse heats the core to billions of Kelvin, and the ambient thermal radiation that's going on there is now gamma rays, and this is terrible because, as we discussed, this leads to photodisintegration of heavy nuclei. This breaks up all of the nucleotides that the star has been diligently collecting, working its way up from hydrogen to helium to carbon to neon ever so slowly, are now completely eliminated, almost completely eliminated, by the hot radiation soup in the stellar core. So whatever has not been ejected so far is pretty much back to protons. At the same time, as the core collapses, the outer layers of the star find themselves unsupported, and at some point there's not what's called a homologous collapse, so the star collapsing as a system. In some sense, the outer layers of the star are essentially in gravitational free fall. They lose contact. They can't respond faster than the speed of sound. They don't know in time that the core has collapsed. And kind of like our slinky, the outer layers find themselves suspended in space with nothing holding them up, and they fall in gravitational free fall, achieving speeds as high as 15 or 20% of the speed of light. So we're being dicey with ignoring relativity in this situation. In the core, as it collapses, we said electron degeneracy has completely been left behind. Electron degeneracy will not support this core. In fact, the pressures are so intense that electrons essentially disappear. They are forced into inverse beta processes so that protons and electrons combine, leaving the star, the core, that is essentially all neutrons. This is not to say there are not protons and electrons left, but their concentrations are severely reduced. We have a very, very neutron-rich soup with this extreme density. Essentially, the core has collapsed to the density of an atomic nucleus and beyond. Does this stop the core? What is left there? That'll be for the next video. In the meantime, what happens in the atmosphere? Well, within about 1/4 of a second, the core is converted to neutrons, and it has achieved this supernuclear density. Notice, 10 to the 17 kilos per meter squared. The core is at this point so dense that even light cannot escape. On the other hand, many of the neutrinos formed in the inverse beta decay carry off most of the energy of the gravitational decay of the core, and there's a lot of energy. This is only a few solar masses, but they are at very small r-squareds. The collapse is very intense, and the power emitted in neutrini for the 10 seconds following the collapse exceeds the combined luminosities of all the stars in the universe. So it's presumably a good thing that neutrini mostly do not interact strongly. This is an extreme luminosity. The density, as we will discuss, is so high that even the neutrino departure takes time. There's a neutrino sphere for a while where even neutrinos are trapped, but they escape first, carrying off the majority of the energy of the collapse. Now, when the core achieves nuclear density or supernuclear density, the core collapse is, I'm giving away the punchline, does stop. And when the core collapse stops, you now have the atmosphere, or the envelope, falling down at relativistic speeds on top of this now rigid core, and this generates the mother of all shock waves. Now, if everything I said were correct, supernovae would look very different than they do, and in fact the details of how the explosion works out are still very much a topic of simulation and debate and research. An important role is played in the fact that this shockwave is highly turbulent. If you really just compress, imagine modeling an atmosphere that's compressing and then suddenly stops, the atmosphere absorbs the shock wave instead of, as we observe, being blown away. What in practice happens is that the shock wave manages to propagate all the way up to the surface of the star, blowing away the atmosphere, blowing away 96% of the mass of a 25 solar mass star. And in the atmosphere of this shockwave propagating, matter is compressed and heated so much that it is here that massive stars reproduce fusion, producing nucleotides all the way up to iron and beyond. So all of the uranium and the gold and the silver, the heavy elements, are produced primarily. There are we talked about S-process nucleosynthesis in heavy stars, and then ejection into the atmosphere before photodisintegration. But another important source of heavy elements is the shock wave in a supernova. And the atmosphere is blown away. It takes a while for light to be able to escape, but as the atmosphere expands and cools a little bit, the opacity is reduced, and then light can finally escape. This takes a few hours, and the luminosity in light, which is, as we'll see, a factor of almost 100 down from the luminosity in neutrini, is still significant. It can be 300 million solar luminosities. So this again is the luminosity of an entire galaxy on the scale of the luminosity of a galaxy coming out of a star. The total energy released is some humongous number, 10 to the 47 joules in light and more in neutrini, and the phenomenon is what is called a type 2 supernova. So we've now seen type 1a supernovae and type 2 supernovae. They're qualitatively different. Remember, a type 1a supernova was essentially a nuclear explosion, the explosive fusion of a white dwarf made of carbon. Type 2 supernova is a core collapse supernova. The energy source is gravitational energy. Essentially, all of these 10 to the 47 joules are Kelvin-Helmholtz energy from the collapse of the core. And so, two very different mechanisms, two different fundamental forces driving these two types of extremely energetic explosions. And can we see these things? Well, with a luminosity of 30 million suns, one would hope so. The most famous one, as mentioned in the quote at the beginning of the title slide of this video, is the famous supernova of 1054 AD. We have records for this from Japanese sources, Arabic sources, even Native American sources possibly. No mention in European sources that I know of, and the very famous Sung Dynasty scholar describing the guest star. And the remnant of the supernova is still visible. It's the famous Crab Nebula in Taurus, M1, the first item on Messier's list of non-comet objects. This is a beautiful recent Hubble image. The filamentary structure and all kinds of properties of this nebula might come up in a future clip. One should note that while supernovae are extremely explosive and energetic processes, it is a bit surprising that the supernova remnant is so luminous 1,000 years after the light from the supernova reached Earth. When the 1054 supernova exploded, it's reasonably nearby. The star was visible for about a week in daytime. So this was a very impressive artifact. There have been Milky Way supernovae 3 times since then, or around that time, in 1006, 1572, and 1604. The estimate is that there's a supernova in the Milky Way every 300 years. Most of them, as most things are in the Milky Way, are far away from us and are obscured by the dust in the disk of the galaxy. So we actually observe many more supernovae in other galaxies than we do in our own, because we can view them edge on and don't have to fight with dust extinction. And another fun example is this supernova in 2011 in M51, the beautiful Whirlpool galaxy, and you can see a before and after shot here, before on the left, after on the right. The arrow points to the bright new star that shows up in the galaxy. That is a type 2 supernova. The fun thing about this one, as with many supernovae of the modern era, is that it was discovered, in fact, by amateur astronomers. There are a lot of us amateurs. I try to count myself among the amateur astronomers, though I don't perhaps qualify. And there's a lot of us looking in a lot of places that the professionals can't all be looking. So more citizen science involvement. Supernovae are we now have seen both core collapse and nuclear supernovae. In general, there's a classification, which, like many things in astronomy, was made before the phenomenon were understood, and so is somewhat weird. The spectral classification is that a supernova is classified as a type 1a supernova. We now know that is the explosion of a white dwarf. If it has strong silicon absorption lines, but no hydrogen or helium in the spectrum. It's a 1b supernova if it has weak hydrogen lines and strong helium lines in the spectrum. It's a 1c if there are weak silicon lines but no hydrogen or helium. And finally, it's type 2, the core collapse we've been discussing right now, if it has strong hydrogen lines in the spectrum. And it turns out, we know what type 1a supernovae are. Those are the nuclear explosion of a white dwarf. It turns out that type 2 and what are called 1b and 1c, 1 because there are no strong hydrogen lines, in fact, are core collapse supernovae resulting from stars that to some extent or other have lost their atmosphere through the mass loss mechanisms we've discussed. So the hydrogen and helium lines are absent or weakened simply because by the time the core collapses, most of the hydrogen and helium envelope has been lost and is not present to absorb the radiation.